This is part 4 of rivets and bolts. At the end of part 3 we determined that the ratio of F4 to F3, well, because F4 times this distance equals F3 times this distance, we determined that F4 over F3 is equal to 3 minus y over 1 minus y. We also know that the ratio of F4 to F3 is proportional to the bearing surface areas. Here's the bearing surface area of F3. There's the bearing surface area of F4. The bearing surface areas are the areas between the pivot point and the two edges. There's the pivot point. Between there and the left edge is the bearing surface area for F3. Between there and the right edge is the bearing surface area for F4. Okay, F3's area has a length of y inches. F4's area has a length of 1 minus y inches. Well, that length times the diameter of the nail would be the area. Anyway, the ratio of their areas is y divided by 1 minus y. That's the ratio of F3's area to F4's area. So the bearing surface area of F3 over F4 is y over 1 minus y. The stress along these areas is likewise proportioned. The stress along the F3 surface area divided by the stress along the F4 surface area is also y divided by 1 minus y, because this wood is being pushed up proportional to y, because there's a pivot point. It's not pushed up at all there. And this wood is being pushed down proportional to 1 minus y. So the force ratio of F3 to F4 is going to be the bearing surface area ratio times the stress ratio, which is going to be y over 1 minus y times y over 1 minus y again. Therefore, F3 over F4 is y divided by 1 minus y, all that in parentheses squared. So let's multiply it out. Y times y gives us y squared. 1 minus y times 1 minus y gives us 1 times 1, which is 1. 1 times negative y, which is negative y, plus another 1 times negative y, which is minus 2y. And a minus y times minus y squared gives us y squared. So that equals that. So we can now flip this equation. Instead of saying F3 over F4 equals that over that, we can just say F4 over F3 equals that over that. So that's what we've done here. Took that and put it on top, that and put it on the bottom. Okay, and we previously determined at the end of part 3 of rivets and bolts that the ratio of F4 to F3 was 3 minus y over 1 minus y. So if F4 over F3 is equal to that, and if F4 over F3 is also equal to that, well then that is equal to that. So let's set that up. We'll put that right here. 3 minus y over 1 minus y equals that, y squared minus 2y plus 1 over y squared. If that over that equals that over that, well then that times that equals that times that. Just like if you were to say 2 over 4 equals 5 over 10, well then 2 times 10 would be 20, would be 4 times 5, which is also 20. No matter what numbers you stick in there, anytime A over B equals C over D, well then A times D equals B times C. So let's say 3 minus y times y squared equals 1 minus y times y squared minus 2y plus 1, which gives us, here we have it, 3 minus y times y squared equals 1 minus y times y squared minus 2y plus 1 from the other page. Okay, upon multiplying the terms, in other words, multiplying this 3 times y squared gives us 3y squared. Minus y times y squared gives us minus y cubed equals 1 times y squared is y squared. 1 times negative 2y is minus 2y. 1 times positive 1 is plus 1. Negative y times y squared is minus y cubed. Negative y times negative 2y is positive 2y squared. Negative y times 1 is minus y. So subtracting 3y squared from each side of the equation and adding y cubed to each side of the equation gives us 0 on the left side. We subtract 3y squared, that gets rid of that. We add y cubed, that gets rid of that. Okay, we subtract 3y squared here, there's 2y squared, there's another y squared, so those disappear when we subtract 3y squared. This negative y cubed, it disappears when we add y cubed to each side. And what we're left with is minus y minus 2y, so minus 3y plus 1, all that equals 0. And if minus 3y plus 1 equals 0, then 3y is equal to 1. And if 3y equals 1, y is 1/3. Now that we know the pivot point is 1/3 of the way across the board, we can say that F4's bearing surface area, which is the other 2/3 of the area from the left edge to the right edge, is twice F3's bearing surface area. This bearing surface area here from the pivot point to the right side is twice the area that this area is, which gives us F3. And we also know that the stress over here averages twice as much as the stress here. So if the area is twice as much and the stress is twice as much, the force is 4 times as much. F4 is 4 times F3. So if F4 is 100 pounds, here we go. If F4 is 100 pounds, then F3 would be 25 pounds and F1 would be 75 pounds. Okay, as mentioned earlier, there's no stress at the pivot point. Here's a pivot point, no stress. Some stress there, twice as much stress here. Okay, the stress at the right edge of the board is twice the stress at the left edge because it's twice as far from the pivot point. You know, that's 1/3 of the way across. We determined that y is 1/3. That's what we just calculated. So if that's 1/3, that's the other 2/3, which means that is twice that. In a double shear joint, if the nail doesn't bend, the stress is maximized along the whole length of the nail, or the bearing surface area between the nail and the wood. So instead of having only 100 pounds of force along the right 2/3, in other words 100 pounds of force between there and there, we would have 200 pounds of force along that area, because in our single shear joint this was pivoting across our pivot point. We had maximum stress here and no stress here. So if we have the same stress all along there, instead of having just 100 pounds, we'd have 200 pounds from here to there. And that other third, being it's pulling up in this double shear, it would give us another 100 pounds. So this joint would hold 300 pounds instead of just 75 pounds. Okay, if you hold a 8-penny nail with a pair of pliers so that the nail extends 1 inch, see there's the head of the nail, there's 1 inch between there and the pliers, extends 1 inch past the pliers, and press it on a set of scales, you'll see that you can push down about 25 pounds when this nail starts bending. Okay, the nail bends at the part held by the pliers right there, because that's where the greatest bending moment is. 25 pounds times 1/2 an inch would only be 12.5 inch-pounds of bending moment right there, but it's 25 inch-pounds of bending moment there, and that's why it bends there. So if this single shear riveted joint here fails because of crushed riveted material, and this double sheared riveted joint also fails because of crushed riveted material, and you have the same surface area across the single shear as you have across the double shear, well then this double shear joint will hold 4 times the load that this one held. we figured that one held 75 pounds and this one holds 300 pounds when the wood is stressed to the same stress level. Of course, if they fail because of rivet shear, this one will hold only twice the load that this one will hold, because there are two places for the rivet to shear as opposed to one place for the rivet to shear on that one. If this nail were sticking past the pliers 2 inches, well then you could press it against the bathroom scales and it would start bending at 12.5 pounds instead of 25, because 12.5 pounds times 2 inches would be 25 inch-pounds, and that's what we've determined that nail can withstand. Okay, in our single shear and double shear joints, the force of the wood pressing against our nail causes bending moments in the nail, just like forcing the nail against the scales causes that 25 inch-pound bending moment up close to the pliers. Let's analyze the bending moments in the nail at various places from the left side of the board, from here to the right side. Okay, there's no bending moment at the left end of the nail because there's no nail sticking past it carrying a load. But as we move to the right, the bending moment increases. At the pivot point, right there, 1/3 of the way across, the bending moment equals F3. Remember F3, it's 1/3 of the way between the left edge and the pivot point. F3 times that distance is what the bending moment is at that point. Okay. Let's assume we're analyzing the same single shear joint we've analyzed previously, the one with a nail going through 2 1-inch boards. Okay, with F3 equal to 25 pounds, F4 equal to 100 pounds, and F1 equal to 75 pounds. Let's say that since the wood is pushing down on the nail left of the pivot point, right there, giving us F3, that the bending moment is negative, making the top of the nail in tension. See, when we push down with F3 here, here's our pivot point. The nail is going to be in tension at the top part, it's going to be in compression at the bottom. Okay, as we look at the bending moments right of the pivot point, the distance from F3 to our reference point, okay, becomes greater. Okay, as we move away from our pivot point, looking at the bending moments here, 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 all along here, the force of F3 becomes further away from our point of reference. So our bending moment contribution from F3 will become greater, but our bending moment contribution from the wood starting to push up on this will start to diminish the bending moment. Of course, the F3 contribution will be more than the beginning of the up contribution until we get to a point about 2/3 over here. Then it starts going back up and it winds up back at 0. It's 0 bending moment at that end of the nail. It's 0 bending moment at this end of the nail.